Our last topic in the stereochemistry is similar to the previous video on resolution. It's going to use the fact that enantiomers have identical physical properties and diastereomers have different physical properties. And this is stereo control in reactions. So is it possible in a reaction to generate one stereoisomer preferable over the other and have what we call a stereoselective reaction? Which will generate one stereoisomer in larger quantity than the other, because it has a lower energy transition state. So both transition states are possible. But because one transition state is slower, it will be selective for going over the lower energy barrier. This is different from a stereospecific reaction, where a single pure isomer of starting material will lead to a single pure isomer of product. And in that case, it's usually the geometry of the transition state that's defined by the mechanism that causes only one transition state to be possible. So what is it that allows some reactions to be stereoselective? So what I want to consider is a fairly simple molecule. Two amino butane. And we're going to start with a single pure stereoisomer of the 2-amino-butane. In this case, R2-amino-butane. Nitrogen is number 1, carbon is attached to it, but carbon is number 2, and methyl group is number 3. Let's think about what would happen if we did a free radical chlorination reaction on R2-amino-butane. We treated this with chlorine. We noted in the first step the chlorine-chlorine bond is going to be broken. That's the initiation step. And then the chlorine radical is going to react with a hydrogen. So I'm going to draw in the hydrogens. And let's just assume for the sake of argument that it's not going to take off the nitrogen-hydrogen bond. The nitrogen-hydrogen bond is stronger than any of the carbon-hydrogen bonds because of the larger nucleus of nitrogen. Just practically speaking, this reaction isn't one that's going to work the way we're going to show it. It's not going to be quite so simple because the amino group will make a mess of things. But let's just think of it as a theoretical possibility. The free radical chlorination of R2-amino-butane would yield a mixture of products. So we can ask ourselves the question, how many possible products could we form from R2-amino-butane? And then kind of what ratio would we expect to find them in? So there are 4 different types of hydrogen in terms of primary, secondary, and tertiary. And there are primary hydrogens on this methyl group that's close to the nitrogen, and primary hydrogens on this methyl group that are different because they're further from the nitrogen. There are secondary hydrogens here, and there's a tertiary hydrogen. But because this is a chiral center, these 2 secondary hydrogens, this hydrogen and this hydrogen, are different distances from the NH2 group. So replacing one of them with a chlorine is actually going to get a different product than replacing the other one with chlorine. And when I take this hydrogen off, I would actually generate a planar radical, which could then cause the chlorine to be attacked by either the top face or the bottom face. So there are actually more possible products then you might think, based on the fact that there's a stereocenter. So there's only one possible product that would result from reacting with either of these three hydrogens, and that's 1-chloro, 2R, 2-amino. And there's only one possible product that could result from reacting with the primary hydrogen on the other end. And that would be 3R. In this case, I would renumber it because now this carbon has something attached to it, and it would be preferred to get to the first attachment sooner rather than later. So this would be 1, 2, 3, 4. This would be 3R, 3-amino 1-chlorobutane, whereas this would be 2R, 1-chloro, 2-amino. And we would expect to form them in roughly equal quantities, because in both cases it's a primary hydrogen that's reacting. If I reacted at carbon 2, I could potentially generate either stereoisomer of the 2-chloro, 2-amino butane. And now there's no hydrogen attached, which means the methyl group is actually the fourth priority substituent. Chlorine outranks nitrogen, nitrogen outranks carbon. So looking from the carbon to the CH3, I would be going from my chlorine behind the board to my nitrogen out in front, and then the one in play. This is the S stereocenter. And this is the R stereocenter. And you know, it should come before chloro. This A comes before C. Those are enantiomers. And that means that the transition states leading to them will also be enantiomers, and so they should be present in equal quantity. If I react at carbon 3, it should be again possible to form two different products, depending on whether the chlorine ends up in front or in back. And so now I have two chiral centers. My first chiral center is untouched. So at the 2 position, it's still the R stereocenter. But now at the 3 position, my chlorine is number 1. The carbon that's attached to nitrogen beats the carbon that's not. So this is number 2. This is number 3. This would be 3R. 2-amino, 3-chloro, butane. And this would be the 3S isomer, where the chlorine is number 1 and then the carbon attached to nitrogen. So this would be 2R3S, 2-amino, 6 possible products that could result. One product from reacting at carbon 1, one product from reacting at carbon 4, but then 2 products for reacting at carbon 2, and 2 products for reacting at carbon 3. Since these 2 are enantiomers, they would be expected to be present in equal quantities. But these last 2 products from reacting at the secondary center are diastereomers of one another, and therefore these would be expected to be formed in unequal quantities. The transition state leading to the enantiomers will be enantiomeric and therefore equal in energy, but the transition states leading to the 2 diastereomers will be unequal in energy because the transition states will also be diastereomeric. So we could ask ourselves the question, which one of these products should predominate? So let's take a look at what the transition state would look like, or what the intermediate would look like for reaction at carbon 2, reaction with the tertiary hydrogen. The mechanism would be such that chlorine would take that hydrogen off to generate HCl and a tertiary radical. That would look something like this, where we now have the NH2 group sticking up. We have a p orbital with a single electron in it, and the molecule is largely planar except for the hydrogens. Looking at it this way, we can see that the chlorine in step 2, propagation step 2, could come from either the right or the left. So the best way to look at the transition states for this molecule will be to redraw this as a Newman projection. Looking down the carbon 2 to carbon 3 bond. If I look down the carbon 2 to carbon 3 bond, the methyl group on the back carbon is breaking up, hydrogen on each side, and then in the front, I've got my NH2 group sticking up, and my hydrogen sticking down, and then I've got my p orbital sticking out like that. That's probably not actually the most stable conformation of that molecule, but you can see that in that conformation, it's absolutely equivalent. Right? These 2 lobes would be the same. So if the radical was over here, then it reacts with Cl2. We would expect to generate a transition state this. We're breaking the ClC bond and forming a CCl bond. And if the radical were on this side, when it reacted with Cl2, this. Again, partially breaking the ClC L bond and partially forming a CCl bond. this transition state is the mirror image of that transition state, reflecting the fact that there's no preference for attacking the one lobe versus the other lobe. And that's going to be true regardless of how you shift this molecule, because if you conclude that's the most stable conformation where the methyl group is hyperconjugating and thus overlapping, there's no preference for that conformation where this lobe would be attached, or that conformation, which is in the enantiomer, where this lobe would be attached. So it really doesn't matter which conformation you decide to start with. This is not the most stable conformation. That's probably the most stable conformation where we get the best hyperconjugation. But it doesn't matter. Either way, you're going to end up with enantiomeric transition states. And if you end up with enantiomeric transition states, you're going to end up with a racemic mixture of products. Let's take a look at what the transition states would look like if you took your original R2-amino butane and reacted the chlorine radical with one of the secondary hydrogens. Again, we have a planar radical. But now we have a chiral center at the adjacent position, where the NH2 group is coming out and the hydrogen is going back. The fact that there's a chiral center here next to the radical means that this molecule is still chiral. Still has the R stereocenter. A chiral molecule would not be expected to react with chlorine in the same way from both sides. So again, we want to look at the Newman projection. And now we want to look at the Newman projection from this carbon to that carbon, because practically speaking, it's better to have our p orbital on the front carbon. So I'm now going to look from carbon 3 to carbon 2, which means the CH3 is down, the NH2 is on the left. I'm just going to flip it like this, and my methyl group is pointing up. Hydrogen is eclipsed with the CH3, and I've got my p orbital. So that's the Newman projection of this planar radical. Probably not the most stable conformation because we have this eclipsing here. And since nitrogen has a lone pair, we might expect the nitrogen atom to be very good at doing hyperconjugation. So we might want to line up one or the other lobe of that orbital with the nitrogen. So I'm going to redraw this. So that my p orbital is overlapping with the nitrogen, so that we can get the best hyperconjugation. Usually we use this little triple equal sign to represent that we haven't changed anything. All we're doing is redrawing the molecule. If I do that, then the hydrogen is over here, and the CH3 group is over there. That's one possible drawing. But I could also draw it the other way. where the lobe that's overlapping with the NH2 group is the other lobe by rotating 180 degrees, which would put the methyl group over here and the hydrogen over there. Those conformations would be expected to be in equilibrium. And this is in equilibrium too, because I did rotate it a little bit rather than just redrawing the identical. So now if we look at these two possible conformations, and we use the radical to attack chlorine, we're going to generate diastereomeric transition states, which are not mirror images of one another, because in one case the two methyl groups are on the same side of the molecule, and in the other case the two methyl groups are on different sides of the molecule. So my transition state in one case is going to look like this. And my transition state in the other case is going to look like that, where there's now partial radical character on chlorine and partial radical character on the carbon. Non-mirror images. Those are diastereomers of one another. Here you'll note that the two methyl groups are anti, whereas over here the two methyl groups are gauche. Which means that this transition state has more steric hinders and should be at a higher energy than this transition state, which has less steric hinders and therefore should be at a lower energy. The product that would result would look like that in this case, and if I then redraw it so that it's in a staggered conformer, so I'm flipping it this way so this methyl group is pointing up, this one's pointing down. The two groups over here, the hydrogen and the methyl group. The hydrogen and the methyl group would be on the same side, and the hydrogen and the nitrogen here would be on the same side. Right? I think that's correct. Maybe not. And then the product of this one, like this. And if I redraw that to put my, well, first thing I want to do is redraw that, it's rotated to put the methyl groups anti to each other. So I get the more stable conformation. So I'm going to move this methyl group over here, the hydrogen up, and NH2 here. And then if I redraw that, it is staggered conformation. So I'm moving it so that the nitrogen and the chlorine will go back when I'm looking at it that way. And the two hydrogens will be up. So you notice that in this case, the NH2 group and the chlorine are on opposite sides of the molecule. And in this case, the nitrogen and the chlorine are on the same side of the molecule. So those products are diastereomers, and this would expect to be the major isomer. And this one should be expected to be the minor isomer. We haven't changed the stereocenter here. That stereocenter should stay R throughout. And in this case, we now have 1, 2, 3. The R stereocenter, and in this case we should have the S stereocenter. Unless I thought I messed up. I did the opposite. This needs to stay the R stereocenter. I accidentally drew the mirror image isomer of what I had drawn here. So the minor isomer would be the 2R3S, and the major isomer would be the 2R3R. So what we're looking at here is an adjacent chiral center directing the stereochemistry. We're going to line up the nitrogen, and we're going to determine that that's a more stable conformation than that. Here we have our methyl groups separated by about as much as we can possibly separate them. And if you look the other way down the bond, right, which is the way I drew them with the NH2 in the back, you can see that there's great separation from the methyl group, whereas if the blue lobe is up, there's really a 15-degree, or a 30-degree rather, dihedral angle here between the two methyl groups. That's worse than an ordinary gauche interaction. It's definitely going to prefer to take this conformant. When the chlorine reacts, it's going to react at the lobe that's not where the nitrogen is, because the nitrogen has a partial negative which would repel the chlorine. So it's going to react with the green lobe from this conformer, but that's not preferred. The preferred conformer looks like this, which means that the chlorine will preferentially react with the blue lobe of the planar p orbital. So we shouldn't expect the transition state coming from attack at the blue lobe here, right, to be the same energy as the transition state from attack at the green lobe. Those are diastereomeric transition states, and diastereomeric transition states are going to be different energy, and therefore cause some stereoselectivity. If I were to put this on an energy diagram, what you see is the radical, in this case the secondary radical intermediate, can react with the one lobe to go over a lower energy transition state, or the other lobe to go over a higher energy transition state. And it doesn't necessarily correlate to the energy of the product. We don't actually have to know where the energy of the product is, because it's the energy of the transition state that causes the selectivity. So we've got a lower energy activation state for reacting with the lobe of the p orbital that allows the two methyl groups to be in this anti-conformation, versus the lobe of the p orbital that forces these two methyl groups to be in the gauche conformation. That's called n-chimeric assistance. And it refers to a chiral center elsewhere in the molecule directing the stereochemistry in an adjacent position. Usually right next to it. But again, the key is that the transition states are diastereomeric, and therefore the transition states have different energies.